just mean a whole bunch of titles. Yeah.
But the real reason is a different one.
Oh, that's an important one. Yeah, should we start?
Hi everyone, we have Chris Heunen with the second category theory lecture.
Yes, hello everyone. Thanks for still being here after a relatively long day of all kinds of new impressions. I'm going to continue on where we left off earlier about categories. The topic of this hour and a half is going to be monads mostly. But just to remember what we were doing before, we talked about categories, we talked about functors, we talked about universal properties, we talked about Cartesian closedness, and especially towards the end, I had to rush it a bit. I'm sorry about that. And because of that, I missed out on a couple of things that I think I need to say because others are going to rely on it later. So before we go to monads, I'm going to recap one or two things. The first one is that I'm making it out as if this is all very clean and neat and everything is easy and you don't have to do any work anywhere. And to some extent that's true, because as we were seeing, often when you try to construct a morphism from some object to some others, you sort of do the obvious thing. And most of the time, that's the right answer. You just have to prove this the right thing. But also, I mean, I was saying also this is a subject that has been developed for, what, 3/4 of a century or something. It is very clean. There's loads of textbooks that I can refer you to that are very nice and clean and easy to read. But at the end of the day, you do have to do some hard work to prove stuff. Most of the effort goes into making the right definitions, and then the proofs are more easy. But there are still proofs. It's just that I'm not showing them to you here because we don't have time to do that. Second thing I want to say is I was claiming at the very beginning that category theory is sort of a way of thinking and it can guide you towards asking the right questions. And especially universal properties are a good example of that. Right? Whenever somebody gives you a category, you could be thinking, does this thing have a terminal object or does it have products or something? But often it also goes the other way around. And I think that's especially the case in programming. You have some sort of construction that does something interesting, something that you're interested in. It might not be the cleanest. It might have all kinds of corner cases. And you're wondering, does this satisfy some sort of property that's maybe universal? Sometimes it will have some universal property on the nose, but often it will be sort of almost like a universal thing, but not quite. And there's some give and take there. Then about universal properties, we talked about this kind of thing for terminal objects. We had a picture here with the color that you could do with numbers if you like, where you want to prove something about the black stuff by reasoning about the possible other black things that are gray, and then there's some unique green thing. You can make that more general. So we talked about terminal objects, we talked about products, and we talked about exponential objects. So let me insert a page here. Because that's an instance of a more general thing that's called limits. And I'm just going to give you a flavor of this because Jules tomorrow or the day after tomorrow, I think, is going to use a specific instance of it that you would like to not have to talk about. And the general idea is this. Oh, come on. There, paste. The idea of a limit is this. Somebody gives you a diagram. This is blue stuff. That diagram can have a limit or it can not have a limit in some fixed category. What is a limit? It's some black object at the top over here, together with all the kind of black maps to each of the things in the diagram that satisfy the universal property, in the sense that if there's any other pretender thing that wants to be the limit, that also has all kinds of maps to the diagram, then there's a unique way that this factors through the limit. And I think the arrow is going the wrong way, sorry. Let me fix that. That's the beauty of modern technology. There, it's fixed. So for example, if your diagram is this, what does it mean to be a limit? Well, that means, first of all, I have an object. I have a map to the diagram, such that, you know, for any other thing, there's a unique thing here. Sorry, this is let me forget that. I want a different example. Suppose that my diagram is empty. So there's no blue points anywhere at the bottom of this schematic. Then what does it mean to be a limit? Well, it's still this black object at the top. There's still a map from this black object to everything at the bottom. So there's no maps. And it has the universal property that if I have any other thing like that, so a gray thing with maps to everything at the bottom which don't exist, then there has to be a unique map from the second to the first. So in other words, that's a terminal object, right? What if my diagram looks like this? Just 2 points, no maps between them, 2 objects with no morphisms anywhere. What does it mean to be a limit? Well, again, I have to have this black thing at the top. Again, I have to have what's called a cone, so mapped from the black thing to all the things in the diagram like this, such that the universal property holds, which means if there's any other pretender with maps to all the things in the diagram, there is a unique, sorry, let me focus myself. Thing like that. Hopefully that looks familiar and you all shout in unison, Chris, but this is only merely a, there you go. Well done. So you can have limits of all kinds of shapes and sizes. This you can specify the diagram at the bottom. You can have all kinds of universal properties like that. And the one that Jules would like to think about is where your diagram looks like this. So then the limit is called a pullback. What is a pullback? Well, it's a cone like that. I could be putting in this one, but I don't have to because all the things, how do I say this? Because part of being cone means that this morphism is the same as that morphism, which is of course the same as that morphism then. So I don't have to put that in, and most of the time people don't. So I'm going to remove it again. Such that if you have any other pretend limit, there is a unique mediating map between the two. And this is called a pullback. If your objects are called A, B, C, let's S, B, C, let's say in set, and the maps are called F and G, then let's say the limit is called L. Then you can compute exactly what this is, namely it's all the pairs of little a's and little b's, such that FA equals GB. Just so you know. This is the kind of thing that you need to prove, right? I'm writing down a formula here. I claim this set satisfies this universal property, but I'm just waving my hands. There's no proof. But you can't prove it, and that's the point. Okay, that's the one thing I missed saying. And the last thing I want to say before we move to monads is I promised. Yeah, shoot. No, wait. Yes, shoot.
So I've seen people say like this category has limits or co-limits. What does that mean?
Mm-hmm. That's a very good question. That means, so having all limits means whenever, for every diagram like that, there exists a limit. So that's the same kind of question as somebody was asking, where did we go? At the very end, What does it mean to have all products? That means for every diagram of that shape with just 2 points, so for every 2 objects, there exists a limit. There is a product. Or when you say, you have all pullbacks, that means for every, 3 objects with 2 arrows between them, there always exists a limit. Right, the final thing I promised before I want to move to monads is to talk about pre-sheaf categories. And here, so I ended by, in the morning, I ended by saying, you have a category of Cartesian closed categories. But what is this thing actually? So I said objects are Cartesian closed categories. Fine, we know what they are. Arrows are functors. Fine, we know what they are. And I claimed this thing, let me put it on a new page. This thing, let's say even cat without the Cartesian closed. So objects are categories. Arrows are functors. This category is Cartesian closed. That's part of the proof of the thing on the previous page about lambda models for simply type lambda calculus being the same as Cartesian closed categories. So I need to prove something here. That means that this category cat has products, has exponential objects, has terminal object. So products, I hope you can sort of guess by now. If I give you 2 categories, you need to construct their product. For the objects, you just take the products of the 2 sets of objects, collection of objects. For the morphisms, you sort of do the same thing. You take pairs of morphisms between the 2 objects. But what about exponential objects? So if C and D are categories, what is the exponential object? This, and it has to be a category again, right? So if we follow the same theme that we had before when we were working with sets, then you might think we're going to take all the things that turn C's into D's, and we call these functors from C to D, right? And that makes total sense. But as I was saying, this exponential has to be an object in cat again, so it has to be a category itself. There has to be morphisms between these functors. So what kind of thing could those be? Well, it stands to reason that if you first just try something, that you could take, so sorry, arrows from F to G, let's say. You could take maps of the form going from F of A to G of A for each object A of C. Right? Because how could you translate one functor into another? You could say for each object, I know that the functor F, you get an FA and a GA, and I want to somehow translate one into the other. I could just ask for a morphism between the 2 in D. That's something you could do, but it turns out that that's a fine category, but it turns out that it's not the exponential object that we're looking for. What you need to make things work is to make this what's called a natural transformation, a collection of such things, such that this holds. Right, so a natural transformation from some functor F from C to D to another functor G from C to D consists of a whole family of maps like this that turn an F into a G. But not just any such family, they have to respect composition. And what that works out to is the following. If you have any morphism little f in C, you can start at FA and go 2 ways. first you could apply the component of the natural transformation, go to GA, and then do G of little f to end up at GB. Other thing you could do is first do f, but on the big F side, and then do the natural transformation now at the object B. And just like before, whenever you can have two different ways of going from somewhere to somewhere else, we're going to ask that these two ways are the same. Right? So that's what it means to be a natural transformation, that this square commutes, that this composition is the same as that composition by every morphism in C. So if you take these things as arrows between functors, you again get a fine category. It's called a functor category. Sometimes also written like this. And that turns out to be the exponential object in cat, making cat into a Cartesian closed category. And now to finally get back to the question, if D is the category set, then these things are called pre-sheaf categories. And they're somehow especially nice because they translate stuff about arbitrary category C into stuff about set. And set, we know, we love, we can work with. Makes things easier to compute. That's the idea of pre-sheaf categories. All right, but that's a bit highbrow. Okay, monads then, or do we have any questions before we go there?
Probably a trivial thing, but how do you form? Yeah, but how do you form the pairs? Like in the pairs case, you said like so given this cat, you have to like given two objects, given two categories, how to form pairs. How do you do that?
Oh, sorry. Yes, I didn't write that down. So when I say this category is Cartesian closed, I have to prove three things, right? Terminal object exists, products exist, exponential exist. This is about exponentials. Didn't write down. Let me move stuff around and make some space. That's not going to fit, maybe here. It's a big jigsaw, this. We'll get there. No. Okay, I'll do it like this. So you're you're asking, what's this? Yeah. And I just said that in words, but didn't write it down. Probably better to write it down. So objects are going to be pairs of A's and B's, where A is an object of C and B is an object of D.
What if C and D are empty? Like, could be the case.
That's fine, because then no such pairs will exist, and then the product will again have no objects.
Because we can kind of like statement like if this C and D have some object, then I should be able to form pair. Something like that.
I'm saying the objects of the product category are pairs of objects from the two factor categories. I guess if you specialize that to empty, then it becomes some sort of conditional. And just to finish, sorry, arrows from A, B to A prime, B prime are pairs, F, G, yes, F, G, where F goes A to B in C and G goes, no, A to A prime, and G goes B to B prime in D. That makes sense?
Yeah, you can. Yeah.
I'll put these slides, by the way, I send them to some people in the organization and hopefully they will do something with it so you can look at them. Okay, on to monads then. So we talked about functors. They go from one category to another. A monad is a specific kind of functor that goes from a category to itself. And why might you want to think about such a thing? if you think about the category as being a model for some sort of types and some sort of computations between these types, or some sort of algorithms, or some sort of computable functions, then the base model only talks about values, like input values and return values. But computations can have more than just values, right? They can have side effects, and that's not captured in this base model. The idea of monads, or at least I use in programming, is to capture this somehow. So you have this base category of pure computations that's only about values. You have a monad on top of that that somehow models what it means to have an extra effect. And out of that, we'll, in half an hour or something, build a new category that does keep the effects, take the effects into account. But just like before, I'm just going to hit you with the definition, and we're going to see loads of examples, and hopefully you'll get the feeling. So what is a monad? A monad, in old terminology, also a standard construction or a triple, consists of some stuff that satisfies some axioms. First of all, a functor that's typically called T, and it goes from a category to itself. Then it has a natural transformation that we just defined, if you remember. That's called eta, whose components go from A to T of A. And another one whose components go from T of A to T of A. Right, that's the data. This one, this natural transformation is sometimes called the unit. And this natural transformation is sometimes called the multiplication or join. And that satisfies some laws that I prepared earlier. And let me copy paste them, and then I'll talk you through them. Such that this. Okay, so a monad is an endofunctor, so some sort of type constructor that turns objects into new objects and turns morphisms into other morphisms, potentially. Together with two ways to manipulate elements, so to speak, of these new types in the form of this unit natural transformation and this multiplication natural transformation. So you can think of T of A as some sort of extra dressed up version of A, right? T has added some sort of effect to the type A. And you can think of the unit natural transformation as some sort of type constructor, if you like, that lifts a value into an effectful type. And you can think of the natural transformation multiplication as some sort of flattening thing, that if you have some base type and two sort of effects have been added to it, it flattens it back down to only having one thing. And that's what these laws are saying here. For example, let's take this one first. If you have some object A, I apply the functor 3 times to it, I get a new object. There's two things I could do, and of course we're going to ask that these two things are the same. First thing I could do is I can take the multiplication at A, which takes T squared to T of A, right? Now T is a functor, so I can take that morphism mu A and apply T to it. That will give me a map from T third of A to T squared of A. And then you can just do the multiplication proper. That goes from T squared of A to T of A. Other thing I could do is I can look at this T third of A. I can realize this is really the same as T squared of TA. Right? It's literally the same thing. So I can apply the multiplication at the object T of A that turns this into a T of T of A, or in other words, T squared of A. Well, that's this one. And then I can multiply in the ordinary way to get back to T of A. These two things I want to be the same. I don't want it to make any difference for how I flatten things out. The same kind of thing for the unit laws. If you start at T of A, there's three things I could do. I could go this way. I could do the identity map on T of A. I can go that way. And I want all three to be the same. Okay, that's the definition of monad. At least that's the first definition of monad. Definition 1. Because sometimes you will see a second definition, definition 2, that says a monad and in this context is sometimes called Kleisli triple. Consists of a functor. That part at least is the same. That you can think of as a sort of type constructor. Again, some sort of natural transformation that we're going to write as return this time. That goes from A to T of A. So that's something like a type converter. Type converter. And a natural transformation that we'll call bind. And sometimes is written infix as greater equal. And this thing goes from T of A to, I'll write it in Haskell notation, to A to T of B to T of B. And that you can think about as a sort of combinator. Combinator. And again, this is a data that has to satisfy some axioms such that I'll just write down the laws. And it's a bit like the laws we had on the previous screen, something about the identity being an identity and something about the, in this case, the bind being associative. So in this case, the laws are this is the same as just applying f to x. So you sort of lift x with the unit, what's it called, constructor, and then bind it with f is the same as just applying f to x. Yes, sorry. Thanks. That's sort of the one, I forget if it's left or right, unit law, and the other one looks like this. T of A bind with return is the same as just T of A. So that's two unit laws, and then the associativity law looks like this. T of A bind lambda x f x bind g is the same as T of A bind f bind g. So this is sort of a one-dimensional algebraic way, equational way of writing down the kind of thing we had here. They express the same properties. This is the way it's implemented in Haskell. If you don't have, if you only have this part, of course, it's called a functor. If you only have these two parts, it's called an applicative functor. And if you have all three, then it's called a monad. Now, these two are two definitions, and I claim they're really the same definition. Let's see if we can fit that on here. Namely, if you give me the definition 1, how can we make this into definition 2? Yes. Microphone?
Can you say what you mean by T applied to small a? I'm a bit confused by that.
Which one over here?
Yeah.
So T is a functor, A is an object in this case.
Isn't that a
Yeah,
type?
well, sorry. No, you're right. I'm writing this. Like that, I guess. I'm not being very precise.
Because we have T of capital A, right? That's a type.
That's the type.
And T of small a
Is a term of that type,
so T of A is a variable.
if you like. So A is a term of type A. T of A is its lift to type T of A, big A.
But isn't this the return? Okay. I think I'll think about it.
I think
When you say the lifting of A, which is a term of type A, into the like I thought that was the whole purpose of the return or unit.
yeah,
But you're saying TA is different than return A, but they're both liftings.
yes, lift is being used in two ways. That's not good use of terminology, sorry. I'm not sure what to call T of A. But this is what I mean. Okay, so if we have definition 1, how do we get the data for definition 2? Oh, sorry, another one?
Sorry, just so they are obviously equal since join is bind is simply map of one of the directions. But what I want to add is, what's the reason why you introduce the second notation if they are equal?
That's a very good question, and I don't really have a good answer. I think this is more a cultural thing where mathematicians have used the first definition, programmers have used the second definition, and both groups are used to the way they're doing things. But I mean, they're the same thing, so there's not really a difference. It's just, I'm not sure how to say this.
But obviously, this is harder to express at the moment since you're saying, I'm emphasizing it here because I can't represent it in the logic you presented so far. So I don't see the motivation for the second.
I'm the wrong spokesperson to advocate the second one.
So I can explain why we tend to use binding in programming languages. There's a very old piece of syntactic sugar for the simplest form of let binding in the simply typed lambda calculus. And you can rewrite that in a way which uses return in one point and bind in another. And it immediately generalizes, so you can slot in the definition of the identity monad and you get the old sugar back. But it works with all monads. And the result is not very far from Haskell's denotation.
That's nice. I didn't know that. Thank you.
I think the thing that causes the trouble is the separation of T of A that comes in from T of B that goes out. So you start having to talk about T of A as if it somehow has elements, as opposed to just talking about relationships between morphisms. I think that's where it's kind of more intuitive if you're thinking of these things as types that have inhabitants, and it doesn't quite fit when you're trying to do the construction more generally for categories where the objects aren't thought of as
Mm.
things which contain values in some way. I think that's the dilemma here.
Yes, that's exactly right.
So the C here, is it some arbitrary category or is something
Sorry,
special
the
about
T, this T?
Yeah, like, I mean the CC.
C. Yeah, that's an arbitrary category. Well,
Okay, so
the problem is it needs to be a category where you can talk about something like terms or elements, otherwise the little a doesn't make sense.
okay, so it has to be some category which has elements or something
Yes.
something like that. Okay, yeah.
But when you have that situation, then the two definitions are the same. Because you can just, if I give you a monad in the form of an eta and a mu, I can build the return and the bind and vice versa. And just to write that down, if you give me, so sort of this direction, if you give me the eta and the mu, you can define the bind of, let me call it x and f to be mu of, no, t of f of x. And I'll let you stare at that to make sure it type checks. And the other way around, if you give me the bind and the return, I can define the mu to be the bind of blank and the identity. And in both cases, eta is just equal to return. So you can translate up and down. If you translate round trip, you get the exact same thing and vice versa. So it doesn't really matter which definition you take if you're in some category where you have something like elements. I'm going to work mostly with definition 1, but everything I say you can translate into terms of definition 2. Okay, so that's fairly theoretical. Definition. Oh, sorry, one last thing before we go to examples is you mentioned the do notation. Let me make that into a remark. Which is useful if you work with definition 2, because then you can write do of a, I'm not sure how to pronounce this, coming from B, something, something, something. That's the same as saying B bind lambda a arrow something, something, something. So that's just syntactic sugar and makes programs a bit more legible. So you can keep unfolding the bind and sort of write it as imperative style. Okay, examples. Oh, sorry. Feel free to speak. In the microphone.
Can I be slightly mean and ask you to give us the instantiation for the identity monad
An instantiation.
of do notation for identity? So you see what I meant earlier.
Yes, you can ask, and I'm going to politely decline. Because I want to do some examples. It's more interesting to see what these things are like in practice and then what you can do with them rather than get stuck on foundations. First example everybody knows is called the maybe monad. So in this case, I have to tell you what t is, I have to tell you what eta is, I have to tell you what mu is. So t of a is going to be, and I have to tell you what c is as well. So the first bunch of examples, c is going to be set, or you can take Hask, or you can take some sort of lambda calculus or anything like that. And for t, I'm going to take this functor that sends a set to a plus 1. So the disjoint union of a with a singleton set. Right, so t of a is just a with one extra point added to it that wasn't there before. And the same for what does t do? It's a functor, right? It has to have map morphisms to morphisms. Where does it send the function f? It sends it to the thing that we'll just write as f plus 1. It does nothing to the extra point and does f as it was before to the points in a. That's the end of functor. Now we have to make a map like eta or return that goes from a to t of a. What does it do? It just sends an element little a to itself and ignores the extra point. And I have to tell you what mu is, which is something of this type. What does it do? Well, if you're in here, I'm going to do nothing. If you're in this part, I'm going to do nothing. If you're in this part, I'm going to do nothing. So this is called a maybe monad because you're computing on some values of type A over there. But it could be that your computation diverges, in which case I want to know about it. There's no good answer. And then I'll just say error, error, error here. I end up in this bit. That's what that means. Now what eta is saying is if you have a perfectly good computation, of course, that's a computation that could possibly diverge. But it will never diverge. You always end up in the A part. What mu is saying is if I have two computations that could possibly diverge, then that's the same thing as one computation that could possibly diverge, because if you never diverge, I know what to do. And there's no difference between the two ways of diverging. Whether you diverge early or diverge late, doesn't matter, you're still diverging. Right? So in Haskell, that's called nothing and just blah, blah, blah. That's the maybe monad. Happy? Okay, second example. Slight extension of this is called the exception monad. Again, C is set. I'm going to stop writing this in a minute. But this time I'm going to take T to be not blank plus 1, but blank plus some fixed set E, where E is a fixed set of exceptions. So again, eta is what it was before. What can we do from mu? It's the same kind of thing. Be something of this type. That's the exact same thing, right? Whether I raise, if I never raise an exception, I know what to do. If I raise an exception early, well, I know what to do. If I raise an exception late, I still know what to do. Again, there's no proof here. You have to check that this satisfies the monad laws, but it will. Actually, this works not just in any category like set, but these two work in any category with what's called co-products, which is a dual of the thing we saw that's called products. But let's not talk about duals because we have enough to do as it is. All right, example 3. This is called the reader monad. Now, T of A is going to be A to the power I for some fixed object or set of inputs. So I need the category that we're talking about to have exponential objects. So set will do, but so will lots of other categories. And I need to fix some object I. All right, what is the unit? It needs to be something of this type. Well, the thing we saw about exponential objects, the universal property is that giving something of this type is the same. Oh, sorry about that. As giving something of this type. And I was claiming earlier, almost always, if I give you a domain and a codomain, there's an obvious way to get from one to the other. what's the obvious way to get from a product to one of the factors? First. So eta is just the curry of first. What is mu? Well, I need to build a map of this type. So I can uncurry that. I don't know why it does that, sorry. So we need to find a map like this. What can I do? Well, now it's slightly trickier. What I'm going to do is keep this first factor intact and sort of do the diagonal map on the second one. Like this. So I just copy the input. And then I'm going to feed one of the inputs to the first input slot and the other one to the second input slot. So in other words, I'm going to do evaluate times identity on I to get me to here. And then I'm going to evaluate again. So if you work out what this does in set, so I can actually write down a function, then what you get is, let me see. Like that. And you can check that this satisfies the monad laws again. Now, clearly, this is called a reader monad because if you have computations of type A, the result of this monad is a computation of type A to the power I. So it takes an input from I and then returns a computation of type A. So it adds the ability to read from the input. Where are we at? Example 4. Opposite of the reader is the writer. So reader gave you the extra ability to read something from an input. Writer is going to give the programmer the extra ability to write something to some sort of logbook or output. You can't always do this. So the obvious thing to do is that, or always some fixed set of object of outputs or log messages of outputs. But for this to work, we need to be able to sequence log messages. If I write one thing to the log, I want to be able to write once more to the log to concatenate the log messages, kind of. So O can't just be any fixed object. I need it to be what's called a semi-group, which means I have to have a map like this that says if I have this log message and then that log matches, then there's a combined log message where I just concatenate the two. And I have to have a map like this that says there's something like an empty message. If I have those things, what might be the multiplication and the unit? Well, the unit needs to be something of this type. So you're given a computation of type A. You want to build some sort of computation of type A that does nothing to the log. What do we do? So forget all the computational interpretation, just thinking categorically, I need to build a map from here to there. I have limited ways of doing that. Basically, all I have is these two pieces of information about O. How could we get from here to there? A product I Um, like this. You can always go from A to A times 1. Why? Because both of these objects, A and A times 1, are products of A and 1. For A times 1, that's sort of by definition the case. But I claim also for this one, that's a product of A times 1. Which makes sense because these two things are isomorphic. I can also always go the other direction and they're inverses. But I always do have this map and we can use it. And once I have this, what was the plan? Yeah, exactly. So if we call this map, I don't know, E for empty and C for concatenation, then this would be identity on A times E. Yeah, very good. And the same kind of thing for the multiplication, which needs to be something of that type. A times O. Same kind of trick. I claim this is isomorphic to A times O, because both are limits of the diagram with 3 elements, 3 objects, namely A and O. So they're isomorphic, so there is this map between them. And once I've written it in this form, of course, I can do the same thing and write concatenation on the O part. Right, so what this monad has done is added the ability to write something to the output, where you can concatenate the output messages and send empty messages. All right, let's keep going. This was example 4. Example 5 is let's combine this, the reader and the writer. You can build something called a state monad. So this time T of A is going to be A times S to the power S, where S is a fixed, oh, sorry, I wouldn't write on the top line. Of states. Why do we think about this as states? Well, if you're reasoning about computations of type A, what are we adding here? The effectful computations are things that take an S and produce not just an A, but another S. Right? So given some state that, let's say, automaton is in, they produce some computation and they update the state. They produce a new state. So it's a sort of stateful computation now. All right. We need an eta, we need a mu. Eta needs to be of this type. And the mu needs to be of this type. What might we do? Okay, so let's think categorically again. I need to build a map from here to there. I have nothing to go on except that this is an exponential object. Yeah. So giving a map like that is you can sort of uncurry it. It's something like this. And of course, now I do have an obvious way to go from A times S to itself, namely just the identity. Same kind of thing for here. All I have to go on is that this is an exponential object, but that's useless because it's on the left. And this is an exponential object, so I can uncurry it. Giving a map like that is the same as giving a map like this. And I want to end up here. How do we get from left to right? Yeah, so I can evaluate which sort of feeds this thing into that input slot. And we're going to be left with A times S to the S times S. And then I can evaluate again. Which is kind of what, if you think about a stateful computation, that's what it should do, right? If I have two state, what do you call this? Evolutions. And the way to make them into one state evolution is by just feeding one to the other. Okay, two more examples, and then we'll have a little break. Example 6, non-determinism. Non-determinism. This time, I'm going to explicitly take the category to be set. I'm going to take T to be the power set functor that we saw before. And I claim this is a monad because, again, the unit needs to be something of this type. Multiplication needs to be something of this type. How can you think about so it's called non-determinism because now, you can choose which of the elements in the subset are gonna happen, and it's up to the devil or the operating system or the environment. I don't know which is gonna happen. But if I have some output of type A, of course, I can make sure that the devil has to choose A by just giving them the singleton set to work with. And the same kind of thing, if I have, how shall I do this? A curly A, which is a family of subsets of elements of A. I could just take the union. Like that. That just sort of flattens the curly brackets, if you like. Right, that's another monad. If you want to implement this in, for example, Haskell, you might not take the power set monad, but you might take the list of A, in which case the multiplication really is just a function concat. And the final example, you might want to add the ability to have probabilistic choices that I know some people in the room do. This time I'm going to take even not just set, but let's say finite sets. No, I think we can take set. Let's just take set. Yeah, I don't know. Let's take set. T of A is going to be the set of probability distributions on A. And so I'm going to say finite support. Right, probability distributions on A. Again, we need to build a unit. And we need to build a multiplication. Sorry. So if you give me an element of the set A, what probability distribution on A could we make go with that? We can take the Dirac distribution. So this time the devil is throwing dice. We just don't give him any choice. We load the dice such that they always come up with the A we want. The multiplication is a slightly more involved formula. Let me write it down for you. It is some sort of integral like that. So that's a sort of convex way of flattening the brackets, if you like. All right, so that's loads of monads we've seen. And just like this morning, we're going to have a little break because everybody's tired. I can tell by the way you're looking at glazed and confused and everything. I had enough for a bit. So talk to your neighbors, talk to different neighbors this time. Just talk to the people in front or behind you or something. We'll get back in 3 minutes and again, we'll switch gears a bit.
Just come back to the T of the small a for just a second.
Yes.
I might. So sorry, because I looked again at like the Haskell Diki and so what would
is it
they
here?
basically,
It's here, right?
So basically they just write for T of A instead they just write M or Y.
Yes.
So it's just a generic variable. And but I think in this case, so if by this T of A you just mean the return
you
of
mean-
pi to A,
You mean
so you would just write Y or something.
this?
Yeah. To denote an arbitrary element of T of capital A.
Okay, let me write a little t maybe,
Yeah,
just because I'm using t instead of.
and so the small t would be just a generic element of T of capital A.
Yeah, that's
And-
probably better.
Yeah, so I think
The same here.
yeah, because if you write capital T of A, so you could say, oh, this is just a return applied to T, but sorry, to small a, but I think this is not the right thing because then you're restricting this to the image of the return, and I think that's too small. So I think it has to be like this.
Thanks. Yeah, sorry, my name is Chris.
So I picked Lumber this week last night. That's why I wasn't there. Yeah, good to meet you. Probably what it takes is not my first movement. Delicate difference right on based on how I used to teach people back in Haskell and so. Yeah, I come from the other side. I come from the man side. No, that's fine. Hopefully that was useful.
Yeah, more like.
The thing I should have known got to is you do know things well on semantics. Yes, therefore immediately putting hey, look, well. But not in had that's the original. And you have to say that still is not combination. I don't know that. It's not good for you know, if you don't know you don't know it's not going to show but if you think you feel the whole moment you see it is I should speak now. I'll sit back there and I don't know if my own well, I think there's stuff on we don't correct. Literal piece of paper.
All right, thank you, everybody. Let's sit down again so we can do the last bit. Everybody talk to somebody new. All right, last half hour, I'm going to talk about what I promised at the start. What's the point of these monads? So you start with an old category and somehow build a new one that incorporates the effects that the monad is supposed to add, so that you still have a nice compositional, clean, modular way of talking about computations now with effects. These things are called algebras for a monad, and there's different ways of doing them. What we're going to talk about first is extreme version, the minimal version of doing that on the one side, which is as small as possible. They're called Kleisli algebras or free algebras. Then we'll talk about the largest possible thing you might want to do. They're called Eilenberg-Moore algebras or just plain algebras, and they're something like handlers for effects. And then if we get to it, we'll talk about anything in between. And because there's again some sort of universal property at play that says this is the initial thing, that's the terminal thing, and there's a resolution for anything in the middle. But let's start with the smallest possible thing. So that's the Kleisli category. If T is a monad on C, actually it's not a definition, I guess it's a proposition. If T is a monad on C, then there is a category, a new category, that's called the Kleisli of T, and sometimes written C with lowercase t. And it looks as follows, with objects are the same as in C. So just A, B, A and C, same as before. But now an arrow in the new category from A to B are arrows, are morphisms from A to T of B in the old category. Right, so you start with an old category in a monad, going to build a new category, objects remain the same, but maps in the new one from A to B are maps from A to T of B in the old one. So for example, if you had the maybe monad, a map in the Kleisli category is going to be something from A to B plus 1. So there's literally a function that could give you a B or it could diverge. And like the exception monad is a map from A to B plus E. So that's either something that you feed an input in A is going to give you an output in B, or it's going to give you some exception, and so on for all the other monads. So I've told you what the objects in the arrow are, and I claim this is a category, but I have to tell you, of course, what the composition and the identity maps are. Right? So that's, I guess, the proof of this proposition. So what is composition? Composition. So you're given a map from A to B in the new category and a map from B to C in the new category. You have to create a map from A to C in the new category. So given a map from A to B in the new category, so that's a map from A to T of B in the old category, and a map from B to C in a new category, so that's a map from B to T of C in the old category. We want to build a map that goes from A to T of C in the old category. What can we do? We don't have a lot to go on, right? We have this map F and this map G. There's only one A anywhere, so let's start by applying F. Okay, now we're at TB. Again, we don't have a lot to go on. The only thing, well, we've used F already. The only thing that we still have to use is this G. But G goes out of B, right? Not out of T of B. Now, luckily, T is a functor, so it can apply it to morphisms. So I can talk about the T of G, and that will go to the T squared of C, right? Because that's what functors do. They map morphisms to morphisms of the right type. So now we're at T squared of C, and I wanted to end up at T of C, so I have one T too many. But I can get rid of that, because T is not just a functor, but in fact a monad. So I can use this multiplication. Right, and that's the composition in the new category. So it uses the multiplication of the monad. And when you try and prove associativity for this new composition in this new category, you need to use the associativity law of the monad to make it work. In a sense, that's why it's there. And in the same kind of way, what are identities? So given an object, I need to find a map from A to T of A in C, in the old category, because that would be a map from A to A in the new category. What could we take? Well, monad doesn't just have a multiplication, it also has a unit. And it turns out when you try and prove the unit laws in this new category, right, so that this unit, when I compose it along this composition with any other map in a new category, you get that same map. To prove that, you use the unit laws for the monad. Like composition on the left gives you the one unit law, composition on the right gives you the other unit law. And that's in a sense exactly why they're there. So they're exactly what you need to make this new category into an actual well-defined legal category. Right, and as I was saying, if you think about the old category as some sort of base category of pure value-based computations, if you think about it that way, then this one will have sort of effectful computations. So that's the point of this Kleisli algebra construction. You can still have a nice category where everything is modular. You can talk about functors into and out of that category. You can translate stuff. You can ask about products and exponentials and all kinds of universal properties. But now with effectful computations rather than just only pure ones. Okay, what does that look like? So we talked about the maybe monad, for example. What is the Kleisli category of the maybe monad on set, let's say? Well, we know objects are the same as the old one, so they're just sets. Just sets A, B, C. An arrow from A to B is going to be the same thing as a map from A to B plus 1. As we saw, functions like this. And I claim another way to think about these things it can be thought of as partial functions from A to B. Right, because you can either end up in the A summand, in which you could say that the function is defined and this is its output, or you can end up in the one summand, in which you say it's diverging, it's sort of undefined. Right, so you can translate back and forth between a partial function from A to B and a total function from A to B plus 1. And then I'm not going to do this now, but if you work through the composition, the Kleisli composition in this new category, that's exactly the composition of partial functions, where, you know, if something is undefined, it stays undefined if you feed it through more partial functions. So in other words, the Kleisli category of may be literally is equal to, not just isomorphic, it literally is equal to this category of partial functions. So in that sense, the maybe monad really adds the ability to be partial. Okay, that was example 1. Example 2. What about the Kleisli of the power set? Monad on set again, let's say. So we know objects are going to be sets, as always. But now an arrow from A to B are functions from A to the power set of B. And just like you can think of functions from A to B plus 1 as partial functions from A to B, you can think of functions A to power set of B can be thought of as relations from A to B. Namely, I can say R is the set of all A's and B's such that B is an element of F of A. And vice versa. I can say F of A is the set of all B's such that what? Such that A, B, and R. So just like in the first example, this is a category we know. Objects are sets, morphisms are relations. If you compute through what the composition in the Kleisli sense is of this new category, it's exactly the composition of relations that we saw. So this category we've seen already, and it's just sets and relations. And I think that's all I want to say about that. Then let me move to the second way of making a new category out of an old one. So we start with a base old category of pure computations that are only based on values. We have this monad that adds effects. I want to make a new category that somehow incorporates this. And this time, what I'm going to do is not just keep the same objects as the old one. I'm going to change the objects. And the objects of the new thing are going to be what's called algebras of the monad, or sometimes an Eilenberg-Moore algebra of a monad T on a category C is it's a morphism. Sorry, it consists, I should stick to my tradition, consists of object, first of all, A and C, some sort of carrier object, and some sort of structure map, which is a morphism from T of A to A that I'll call little a. So this is called the carrier object. Now this is called the structure map. Such that some diagrams commute. What are these diagrams? They are these ones. Sorry, these ones. Right, so this falls from the sky. I'm not going to try and motivate that. I think there will be some talks later in the week that talk about effects and handlers. I'm going to leave it to them to motivate what this means, but think about it that way. So for example, if T is a maybe monad, then an algebra is something that says it's some sort of type A with the ability to interpret divergence within A. So it has this map that can handle not just A's, but also divergence. Or in the case of exceptions, it can handle exceptions. So this is a thing. And we're going to make these things into the objects of the new cat. Sorry, question?
How's the big A related to small a? Is this just like a?
Big A is some object, little a is some morphism of the type. Domain is T of big A, codomain is big A. Other than that, there's no relation.
Where usually you put the F. Got it.
Yeah, we could call it F, but I want to emphasize that the two things go together. But there's no relationship between them other than that the type of little a is you know, this. All right. What was I going to say? Yes. Okay, so I guess that's a proposition again rather than a definition. There is a category that's called EM of T, or sometimes C to the superscript T, with objects are algebras as above, and an arrow from one algebra to another algebra are, I think I prepared this one. Maps in the base category such that something commutes. And like all these diagrams that I'm showing you, it's always the same kind of thing. You have some sort of canonical way to get from here to there. There's another way. We want them to be equal. And it will turn out later, this is exactly what you need to make a composition well defined later on. So this is a proposition. I claim this is a category. You have to say what the composition is. It's just going to be a composition of these things. You have to prove that it satisfies that again. I'm going to give you an example without talking it through. If we look at what are the algebras of the power set monad, then you can compute everything out. So let's think about first what an algebra for a power set monad is. So it's a structure map like that, right? So that means it's a function that takes a subset and produces a element. And the way I'm going to think about this is taking the supremum of that subset in some sort of partially ordered set. Because I claim this Eilenberg-Moore category is the category of complete lattices, whose objects are, well, complete lattices, so partially ordered sets, such that for every subset, there is a supremum. How do we write this? Now let me write it out, such that there is a P in P such that, oh, this is, I shouldn't be writing this out. Let's such that each subset has a least upper bound. So the structure map is exactly what gives you the least upper bound. And I'll just leave that for you to think about if you would like to do that. Now we have about 10 minutes left. I have a topic I want to tell you about, but it's going to be slightly rushed. So I'm thinking maybe we do that tomorrow morning. Or, okay, let's do some questions, yes.
Doesn't normally an algebra just require a functor? Why is it here a monad?
Oh, yes, that's a good point. People also talk about algebras and co-algebras for functors. That's a totally valid, what do you call this? A state of play, piece of art. research area. They're also called algebras. But things work nicer when the functor in play is a monad. You can still, if it's just a functor, or not even an applicative functor, you can still talk about initial algebras and that kind of thing. And you can think about them as some sort of algebraic data structure. But somehow, if you want to be able to especially combine effects and make them modular and have compositions again, then having the functor be a monad makes things nicer. Yes, I should have said that. Thank you.
So,
Yeah.
yeah, I got maybe it's more of a clarification. When you say the objects are EM algebras, you're saying all the EM algebras I can find there. It's
Yes.
maximal in some sense. Is that right?
Yes.
Okay.
So just like the category of sets, any set whatsoever you can find on the street anywhere will go in. That's allowed.
Okay.
So just like here, objects are just any EM algebra you can find for this monad. It could be that there's none. Could happen. But it could be that there's loads and loads.
For the example at the bottom there, where you say that the EM algebras of power sets are complete lattices, couldn't you very well consider an EM algebra that doesn't happen to be defined in that supremum way? For instance, you could just as easily take the inverse relation, so it's the infimum, and that wouldn't be what you defined there with it all always being a least upper bound, but it would be defined in a different way.
That's a very good question.
Or any other way of selecting a single element out of a subset.
That's a very good question. I'm going to have to give you an answer in two parts. First of all, when I write down this equality, that takes a proof, right? What I've been arguing is if I give you a complete lattice, you can think about that as an algebra. So that's an inclusion from here to here, kind of. What I didn't talk about is an inclusion from left to right. That takes more proof. I need to think about that. But basically, the intuition behind that proof is that if you have one of these structure maps that satisfies, that, and the monad is associative and all that, where did it go? This monad law about associativity. This one. If you work out what this means and you think about that as a supremum thing, then this structure map is idempotent in the sense that if I sort of do it twice, that's the same as doing it once. So like the maximum of of x and y is the same as the maximum. Sorry, you know what I'm trying to say. Let me not try and say it in formulas and words. And then you can just, if you have any set with a structure map like that, that's idempotent and commutative, which you can also prove, then it's just algebra to get to it must be the supremum of something. Second part of the answer is, yes, you could also have taken infima, but what I didn't tell you here is that if you look at the arrows, because we also know what the arrows of the Eilenberg-Mora category are, there's things that preserve not just, so functions that reserve arbitrary suprema and finite infima, because every complete lattice has all suprema automatically also has all infima arbitrarily big, including finite ones, but the morphisms only need to preserve the finite infs. And that just falls out of the details of what you look at when what the morphisms are.
Can you go back to that slide where you proved that the cat is Cartesian closed?
Yes, I can. Where are we? Somewhere here? This?
Yeah, so in the exponential part, so I don't fully get it, but so if I remember correctly, you mentioned that something like here, like in the exponential case, you use the specific category of sets somehow to prove something about arbitrary sets. Sorry, arbitrary categories, something like that. So what was pre-sheaves again? Like how,
Oh, I see what you mean. Yes, I didn't write that down. So what I've written down here in blue is just saying that the category cat is Cartesian closed.
Yeah.
Because it has products, it has exponential objects.
Yeah.
What I then went on to say but didn't write down is, yes, I'll stop after this. So if you look at C set, that's called a pre-sheaf category. So that's an example of such a functor category where you specialize D to be set.
Okay, so,
And they are especially nice. And let's keep it at that.
okay.
Okay, lightning talks.
Let's take a 1 minute break while we set up. So don't leave your seats, but feel free to talk.